Welcome back to our lesson on acids and bases. We've been practicing the neutralization reaction between an acid and a base, making a salt and water. And in the next part of our lesson, we are going to consider the chemistry where we write a reaction known as a molecular equation, turn the molecular into the ionic equation, and then moving that to what we would refer to as a net ionic equation. And to represent this with the first example, we'll show hydrobromic acid with barium hydroxide. What I'd like to do is to write these equations with you, and we'll do that just kind of extending the page and starting over. So we're going to take an acid. An acid starts with an H, and the acid we'll begin with is hydrobromic acid, HBr. Hydrobromic acid. And if I'm just thinking about making sure I had that right. Yep, hydrobromic with barium hydroxide. And so now our next reactant would be barium hydroxide. And I'm just reviewing a little bit of the chemistry that we practiced in our first recorded lesson. We know that an acid reacts with a base. Acids start with hydrogen ions. So H is a +1, bromide is a -1, HBr is an electrically neutral compound based on charge, hydrobromic acid. We understand that a base ends with hydroxide, OH negative. OH is a polyatomic ion, carries a -1 charge. The barium has a +2 charge, so that's why you see it being crisscrossed to create an electrically neutral compound. When an acid reacts with a base, we take the H and the OH and we neutralize. We have HOH. We understand that that's written as water, but sometimes I like to just write it as HOH to remind us that the hydrogen ion came from the acid, the hydroxide ion came from the base, and we create an electrically neutral compound known as water, H2O. And we make a salt. And the salt here starts with the positive barium ion, Ba. It carries a +2 charge. And the bromide, the negative ion over there, Br, -1. And so we can see when we crisscross, we get Ba, Br2, barium bromide. And then to balance, remember how we had 2 base ions, so we're going to need 2 acid ions to neutralize those, creating 2 water molecules. We end with a 2-to-1, 2-to-1 ratio. What we just wrote is known as a molecular equation. The molecular equation shows the acid reacting with the base, forming a salt and water. But we understand that when we place these strong electrolytes into water, we ionize. We take the strong acid and the strong base and the strong electrolyte here, the salt, and we're going to show them in their ionic form. When HBr is placed into water and it creates an aqueous solution, we understand that the water detaches or separates those ions from each other. We get 2 aqueous ions of hydrogen. Notice the 2 from the stoichiometry here. The 2 is the coefficient, 2 units of H+, and we would get 2 units of the negative ion, Br negative. 2 hydrogens and 2 bromides. This strong electrolyte dissociates or separates into its ions. And the barium hydroxide is also a strong electrolyte, and we know that electrolytes simply mean that they break apart and form their aqueous ions. That we would have an aqueous ion of barium and 2 aqueous ions of hydroxide. So in the water solution, we're breaking apart the strong electrolytes, forming their ions. 2 hydrogen ions from the acid and 2 bromide ions from the acid are reacting with a barium ion from the base and 2 hydroxide ions also from the base. Now, water is a non-electrolyte. It's a molecular compound, isn't it? And molecules stay together. A non-electrolyte does not break apart in ions. But here we have a strong electrolyte in our water-soluble salt called barium bromide. And so we're going to dissociate that barium bromide into its ions. So we have 2 hydrogens, 2 bromides, a barium, and 2 hydroxides on the reactant side, forming water. Oops, I forgot the coefficient. Let me put that back there. 2 waters, a barium, and 2 bromides. What do we notice the same on the left and on the right side of our equation here? Do you notice that a barium ion, Ba2 positive, appears on the left and the right side unchanged? Do you also notice that the bromide ions also appear on both sides of the arrow unchanged? These are what we refer to as spectator ions. Spectators, just as in the, an analogy of athletics, they're in the stands watching, they're not down on the court participating. So a spectator ion is in the solution, but it did not undergo a chemical change. They remained the same from the left to the right. And when we get rid of the spectators, we can show just the chemistry of the reaction in what we refer to as a net ionic equation. The net ionic equation simply eliminates the spectators and shows just the chemical change. We had 2 hydrogen ions, 2 hydroxide ions combining to form the neutralized water molecules. And if I take those 2's, 2 H positives, 2 OH negatives, 2 waters, and I simply reduce them down, the 2 to 2 to 2 ratio, and just represent that as a single hydrogen and a hydroxide combined to make water. The acid ion and the base ion neutralize to make the water. This is what the net ionic equation is for an acid-base neutralization. We take the acid protons, combine them to the base hydroxides, and show the formation of the neutral water molecule. And that's exactly what this slide did for us, but it allowed us to kind of go through step by step. The molecular equation shows the acid and the base forming the salt and water. We broke it apart in dissociated form and then just shown those spectators here, the bromides remaining constant, the bariums remaining constant. We eliminated those and just showed the chemistry of the combination of acid to base making water. And when we considered the vocabulary we just shared, we kind of seeded that next slide as well. We went from the molecular equation to the ionic to the net ionic by eliminating what we called spectator ions. And we circled those on the last screen as well. Bromide remained unchanged from the left to the right. Barium remained unchanged from the left to the right. They did not undergo a chemical change. Therefore, they're known as spectator ions. And when we eliminate the spectators, we went from the molecular equation to the ionic equation to the net ionic equation by eliminating the spectator ions. Barium and bromide produced the salt. Barium bromide was the salt. And we eliminate those 2 ions. We show just the chemical change in the formation of the neutral water molecule. Acids and bases neutralize one another to make a water. Let's take a peek at what this might look like in your sapling homework. Let's write a net ionic equation for the following reactions. Well, the first one we see is HBr. There's our acid, HBr, reacting with BaOH taken twice. Does this look familiar from our last screen? It just happens to match the example that we just worked through, doesn't it? I know that HBr is the acid. It starts with an H. And barium hydroxide is the base. And the base is those things that end with hydroxide. The pattern of chemical change says H and OH are going to neutralize one another to form a water. I like to write water as HOH just so I can remember that the hydrogen and hydroxide, this came from the acid, this came from the base. And the salt would be barium bromide, barium with its +2, bromide with its -1, and there's our salt. When an acid and a base neutralize one another, we get water and salt. And just to remember how we balanced that equation, we took the barium hydroxide with its 2 base units and knew that we had to have 2 acid units to neutralize to make 2 waters. And so when we go from that molecular equation to the net ionic equation, we understand that these acid ions dissociate, the base ions dissociate to make a water, and the spectators are going to be the barium and the bromide. And so we can simply show the acid proton combining with the base hydroxide forming water. And the reason I eliminated the 2 to 2 to 2 on our coefficients here, we had 2 acids, 2 bases, and 2 waters. We're just going to write that in the lowest ratio possible. How about HNO3, nitric acid, with strontium hydroxide? So again, we see a very similar pattern, don't we? We have HNO3, which is called nitric acid, with strontium hydroxide. To finish the molecular equation, we know that the acid ion and the nitrate ion are the components here. So NO3 is that polyatomic ion called nitrate. And we'd have strontium hydroxide as our base. When we neutralize, acids and bases combine to make water. So we have HOH, there's our water molecule. H is a plus, came from the acid proton. The base ion hydroxide, we understand is H2O, it's water, but I'm going to write it as HOH to remind ourselves it's part acid and part base. And the salt, of course, would be strontium nitrate, SR, strontium, it's a +2. Nitrates are polyatomic -1, so we get SrNO3 taken twice. And you can clearly see that since there's 2 base ions, we're going to need 2 acid ions to neutralize and create the waters. And so therefore, you see the very similar pattern here. 2 acid ions, 1 base here. We end up having the very same net ionic equation. This is a strong electrolyte. It 100% dissociates. To dissociate means it created 2 hydrogens and 2 nitrates. This is a strong electrolyte, and by that I mean it dissociates when it goes into water. We're going to create a strontium ion and 2 hydroxide ions. Water is a non-electrolyte. It does not dissociate and therefore remains together in its molecular form. And the salt, of course, here is also a strong electrolyte. So we get strontium ion and 2 nitrate ions. So here we have hydrogen ion combining with the base ion forming water. What are those spectators? Well, you're right. They're the items that remained unchanged from the left to the right. They're going to be the ions involved in the formation of the salt, strontium nitrate. These are what are referred to as the spectator ions. So when we write out our net ionic equation, we have the same answer as above, don't we? We're going to reduce the 2's and simply show the formation of a water from the proton from the acid, the base ion known as hydroxide, forming the water molecule. And there's our net ionic equation. An acid neutralizes a base to make a water. Oops, I hopped over. Let's see if I can back up. There we go. Practice from sapling again. Here we see an example. Acids react with carbonates to form carbon dioxide bubbles. Now, what we have here is very similar to that opening slide we began with the calcium carbonate coming from the coral reefs being decomposed by acid rain. We're going to have a similar example. So here I'm noticing we have sodium, and this is hydrogen carbonate, sodium bicarbonate. It's commonly referred to as baking soda. We're reacting it with an acid, acetic acid, which is commonly referred to as vinegar. And what we're going to see actually are carbon dioxide bubbles. Let's go through this step by step so you can see the chemistry that's occurring. So here we have baking soda. I'm going to write that out. NaH, sodium. It's a positive ion. Na is a +1. And the last name is bicarbonate or hydrogen carbonate. It's on your polyatomic ion. This is not necessary, but I'm just showing a parenthesis here to remind us that this is a polyatomic ion, a group of atoms carrying a charge. Hydrogen carbonate is all one ion and it carries a -1. So baking soda we'll put in as a solid form. So that little S tells me its state of matter is solid. Sodium bicarbonate, sodium hydrogen carbonate, baking soda. We're going to pour vinegar on that, which is acetic acid. Acetic acid says acids start with an H, it's a +1. And we have a polyatomic ion called acetate, C2H3O2. And again, not necessary, but I'm going to put it in a parenthesis so we remember it's a group of atoms acting as a unit carrying a charge. The name of this polyatomic ion is called acetate. Do you see it on your polyatomic ion chart? It carries a -1 charge. And this is called, just so we can see it written out, is called hydrogen carbonate. Hydrogen is sometimes referred to as bi, so sometimes you see that as bicarbonate or hydrogen carbonate. Sodium bicarbonate reacts with vinegar, acetic acid. Now it's the same chemistry. Notice that we have a positive sodium, Na+, and the negative acetate, C2H3O2 negative. Sodium acetate will become our salt in our double displacement reaction. We're taking the two positives and exchanging their places. So sodium will hook to acetate. So one of our very first products here would be Na, the positive ion, Na+, and the negative ion, C2H3O2 negative. This is called sodium acetate. This is our salt that we produce. And back over here, when H from the acid combines to the HCO3 called hydrogen carbonate, we get HCO3. I'm going to combine those, HCO3. I'm going to combine those simply to be H2CO3. Alrighty. So here we have an aqueous acid reacting with solid baking soda. We're going to get an aqueous salt, H2CO3 here, this NaC2H3O2. This is our aqueous salt. And we understand that as soon as this acid forms, it's very unstable, and as we predicted from our very first introductory slide, we understand it decomposes. It's going to break apart or separate into carbon dioxide and water. So as soon as it forms, it breaks down. So it's no longer there. We're going to separate it out into carbon dioxide gas and liquid water. So our molecular equation for this particular reaction, the entire products here, NaHCO3 reacts with H, C2H3O2, forming Na, C2H3O2, and CO2 gas and water. So there's three products here: sodium acetate, carbon dioxide, and water. And if we turn that into a net ionic equation, remember the spectators? The spectators will be those ions involved in the salt. And so we have, thinking about the chemistry here, we'd have hydrogen ion with your bicarbonate ion forming your carbon dioxide and water. Now technically this is a weak acid, so if it's weak, we typically see this left together and not separated. So the true chemistry would leave that acid together and not separate it out, because we only separate out the strong. So the strong electrolyte of sodium hydrogen carbonate would be dissociated. A strong electrolyte such as the salt would be separated. And of course, carbon dioxide and water are both non-electrolytes. And so to finish this correctly, we would still point at the carbon dioxide gas and the water, but you'd also have in solution that acetate ion, because the acid itself did not start as a strong electrolyte. So since this is a weak electrolyte, we're more correct to leave it together in its molecular form, break apart only the strong electrolytes. So we have aqueous acetic acid with aqueous bicarbonate ion forming carbon dioxide gas, liquid water, and the aqueous ion of acetate. The driving force would be the bubbles. That would be the observation you'd see to know that a chemical change took place. Acidic solutions have pH levels below 7, as we mentioned. Acidic solutions have more acid ion compared to base ion, that the molarity or the concentration of the acid ion is greater than base. A basic solution would have hydroxide ion in a greater concentration than hydrogens, and its pH would fall above 7. And a neutral solution is one where we have exactly the same concentration of the acid ion as compared to the base ion, which would be exactly 7.0 on our pH scale. So we're about to introduce the concept of measuring how acidic or how basic a solution is with our useful relationship called the ion product constant for water. The constant gets a letter K for constant, and the little W represents the water concentration. When water self-ionizes, and again, just thinking about water breaking apart into its ions, we get H plus and OH negative. The ionization of water. If I take a water molecule and form its ions, we could see the acid ion forming the H plus, and the base ion forming the OH negative. We get equal parts acid and base in our solution. Well, if we were to measure the concentration of how often this happens in an ordinary cup of water at 25 degrees Celsius, which is approximately room temperature, we would get exactly, the same amount of hydrogen ions, 1 times 10 to the negative 7th molar units of hydrogen ion, and 1 times 10 to the negative 7th molar units of the base ion. In an ordinary cup of water, some of those water molecules self-ionize. They break apart. And when they do so, not very many, but some dissociate. Now keep in mind, 1 times 10 to the negative 7th is 0.00000001. That's what that number means. That's not very many molecules, is it? But you're starting to see the development of a pH scale. A pH scale is a logarithmic function. That means just base unit of 10, and it's going to relate the power of 10 that you see. Because water, which is a neutral substance, equal part acid and base, has an exponent associated with it of 7, we're starting to see why 7 is the basis of calling something neutral. When we multiply 1 times 10 to the negative 7th by itself, that's where we get the product. Product means to multiply. We get the product called 1 times 10 to the negative 14th. The top of the pH scale is the power of 14. So another way to look at this, it says, when we consider water ionizing, water collides with itself to ionize, we get an acid H3O+, remember how we called that hydronium, the acid ion or protonated water, and the hydroxide ion. They come out to be exactly 1 times 10 to the negative 7th molar units. They come out to be 1 times 10 to the negative 7th molar units. pH of 7, we'll soon learn, is a neutral solution. So a pH, we will see, is defined as the power of 10. So we're going to see negative log of the concentration of the acid ion, which we could write as H3O+ or simply H+, negative log of the acid ion, hydronium or hydroxide. And so what we start to look at is we consider pH scale. What power of 10? Now notice we put negative in front of the log so that we can end up having a pH value that's in a positive number. Let's take a practice. pH is a solution. It's in a measurement of the concentration of H+. And here's our formula. The H+ ion in a molarity unit, and I'll just keep talking while this wheel is spinning here, the negative log of the concentration of H+, and what we have there is a concentration unit known as pH. Molarity, remember, is moles per liter, and moles per liter, what we'll end up taking is negative log of hydrogen ion. Since pH is a log scale based on the power of 10, remember that a pH change of just 1 unit actually is a quite significant difference. So a significant difference between a pH unit of 6 and 7 or 2 to 3. So let's kind of see what this slide is actually representing. If we have a pH scale in which 7 is neutral, and I have the hydrogen ion concentration is what we're measuring, a pH of 7 would have a concentration of 1 times 10 to the negative 7th molar units for the hydrogen. And if I go down the scale and call a pH of 6, it's becoming more acidic, we have 1 times 10 to the negative 6th molar units for the concentration of hydrogen. This unit, pH of 6, is actually 10 times more acidic than a pH of 7. And if I go down the scale one more number, a pH of 5, that's 1 times 10 to the negative 5th pH units. So a pH of 5 compared to 7 is actually 100 times more acidic. See how things significantly change. Here we have a pH of 4. That's like writing 1 times 10 to the negative 4 molar units. If I go from pH of 4 to a pH of 7, we're moving 3 places on a power of 10. It's 1,000 times more acidic. So you can see a significant change in pH, even though the number line doesn't appear to be changing that much. Remember, it's a power of 10. So a solution of a pH of 2 is 10 times more acidic than a pH of 3. And it works if we go up as well and become a basic solution, where now we have more hydroxide ion compared to hydrogen ion. Hydrogen is becoming smaller and smaller. If I have a pH of 8, the concentration of the acid ion is 1 times 10 to the negative 8th. It is, if I consider this, it's 10 times more basic than compared to neutral water. Or water is 10 times more acidic compared to a pH of 8 solution. So we're looking at the relationships of Kw, the ion product constant for water. pH is a measurement of hydrogen ion. Remember that if it's exactly the same, we have a pH of 7, because we would have 1 times 10 to the negative 7th of hydrogen and 1 times 10 to the negative 7th of hydroxide. Knowing that they always add to 14, our solution is acidic. Our solution is neutral when they're exactly the same. What I look down here is if it's acidic, let's suppose we have more hydrogen. If we have 1 times 10 to the negative 5th, let's just decide, what would the concentration of hydroxide be? Knowing that they always add to 14, we would have a negative 9th concentration of hydroxide, because their product is always the same number, 1e negative 14. So think about that. We have 0, 0, 0, 0, 1. That's 1 times 10 to the negative 5th as your hydrogen concentration. You would have 1, 2, 3, 4, 5, 6, 7, 8, 9. There is your concentration here of hydroxide. Those two values, when multiplied together, 1e negative 5 and 1e negative 9, give me this constant, the top of our pH scale, 1e negative 14. You can clearly see that this is a bigger number as compared to this value. When hydrogen is bigger in amount as compared to hydroxide, our solution is acidic. And if we just flip that analogy here, if we have a greater concentration of base ion as compared to acid, we would have a pH greater than 7, giving us a basic solution. Our pH measures the concentration of acidic solutions and basic solutions, but remember, pH is always based off of the concentration of the acid ion H+. There is a logarithmic function for the base ion, and we could take negative log of hydroxide concentration and get something called POH. pH, when added to POH, always adds to 14. P is a mathematic function. It just means take the negative log. If you see P, it means negative log. So pH, negative log of hydrogen. POH, negative log of hydroxide. That's the true mathematic definition of the algebra expression of P. It just simply means take a negative log. And so the value of pH and POH will always give me 14, the top of the pH scale, the ion product constant for water. Here we have pure water with a pH of 7, 1 times 10 to the negative 7th molar units of hydrogen ion. Milk is slightly acidic. Tomato juice, even more acidic. Coca-Cola, lemon juice, and stomach acid are all examples of everyday products of acids. Look at some of the bases. Ocean water, seawater, is alkaline. It is slightly basic, a little above 8. Milk of magnesia is a medicine used to neutralize acids in your stomach, a pH of about 10.4. Household ammonia is a cleansing agent, isn't it? A pH of over 11, just slightly below 12. An oven cleaner such as lye, sodium hydroxide, a pH of about 14, very strong base. Now, remember our big umbrella of our chapter of why we're studying acids and bases. Our chapter is called Acid Rain. If normal rain is slightly acidic, look here, here's normal pH of 7. I'm really going down the scale to get normal rain is slightly acidic. But the acid rain, those things that are considered too acidic for environmental harmony, have a pH range of below 3, about 2.8, all the way to about 5. So acid rain or acid fog, those things that when the normal rain is dissolving gases to create acid, it's changing the pH. So in other words, when water, in terms of rain, falls and it dissolves, let's say, carbon dioxide, it's going to form an acid, H2CO3. If water falls from the earth or from the sky to the earth and dissolves, absorbs some of the sulfur dioxides, we're going to form an acid, H2SO3. Or if water falls from the sky and absorbs nitrous oxides, so we could just say NO2, we're going to form an acid, HNO3. So these gases being either, gases in the atmosphere that occur naturally, carbon dioxide, or in terms of being placed into the atmosphere by environmental industry, we would have, these sources of acid rain. To measure the pH in basic solutions, we often use an expression to calculate either H plus or OH negative. And so we're just reminding ourselves of those relationships we've been studying. H plus is equal, we call it neutral. If we have more acid, we call it acidic. And if we have more base, it's a basic solution. Let's take a peek at what a practice sampling question might look like. We have hydroxide ion concentrate. What is the hydroxide ion concentration in an aqueous solution where the acid concentration is 1.5 times 10 to the negative 14th? So here's what we know about that relationship. We know that we have an ion product constant for water. And it mathematically is equal to 1 times 10 to the negative 14th. That's the product constant. Always the same number, constant. If we have the concentration of acid is 1.5 times 10 to the negative 4th molar units, what is the hydroxide ion concentration, OH negative? So here we know a constant, Kw, and we're given one of the two ions. On your calculator, we're going to hit 1 times 10 to the negative 14th, and we're going to divide out 1.5 times 10 to the negative 4th molar units, and that will provide for us the concentration of the base ion, OH negative. On my screen on the calculator, we're going to hit one scientific notation key is EE. Make sure you remember the negative 14. And you're going to divide that by 1.5, find your scientific notation key, negative 4. And be sure to hit this with me right now to make sure we're hitting the same way and getting a common answer. My EE sits on top of my comma key, so I have to go second function, EE, and I have negative 14. I'll divide out 1.5, scientific notation key, EE, and that's to the negative 4th power. My screen says 6.6 repeating, E negative 11, so we'll put 6.67 times 10 to the negative 11th molar units is our concentration of the base ion. Clearly you see that the acid ion is in greater concentration than the base ion, and our solution would be acidic. The concentration of H plus is a bigger number than the concentration of the base. A power of -4, that's this number written in a decimal form. And this is this number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimals, and then the 6, 6, 7 repeating. This is a much smaller number, that's a 0, not a 6, compared to this. So when acid ion is in greater amounts, we have an acidic solution. It didn't ask us to, but it certainly would be easy to calculate the pH. We would simply take negative log of the concentration of the acid ion, 1.5 times 10 to the -4th molar units. And if I hit that, let's do it together. Hit your negative and then your LOG key. Don't hit LN, that's natural log. You want LOG, negative log, and then inside that parenthesis, 1.5 E -4. Close your parenthesis on your calculator, and does your screen match mine? 3.82 pH units. And clearly that pH number is below 7, which makes sense because we predicted this solution to be acidic. Practice sampling some more. Classify the solutions as acidic, basic, or neutral. I suggest we calculate the pH, and we'll do that by calculating the negative log of the provided answers here, these values, and we'll get a pH number. And we know that pH, if it's less than 7, is acidic. If it's greater than 7, it is basic. And if it is exactly 7, it's neutral. So let's hit negative log of 1. So here I'm going to clear screen. Negative log, and then in your calculator go 1e -8. Close your parenthesis. Negative log 1e -8. That's your scientific notation key. Do you notice how the pH? It came out to be exactly 8. 8.00 my screen says. Well, that number is bigger than 7. This solution is basic. What is the pH when the hydrogen ion equals 1 times 10 to the -2? So negative log on your calculator, 1e -2, close your parenthesis. Negative log 1e -2 gives me a pH of exactly 2.0. That is a number less than 7, so here we have an acidic solution. We'll do one more. Negative log, on your calculator, hit negative log, and how many zeros are there? We have 1, 2, 3, 4 zeros, so 0.00001 in your calculator, and that pH came out to be 5. And that makes sense. You have 1, 2, 3, 4, 5. That's 1 times 10 to the -5th. The pH is 5. Are you noticing that trend? pH of 8, pH of 2, pH of 5. So this solution is also acidic, a number less than 7. Calculate the pH. pH is defined as taking the negative log of the concentration of the acid ion, H+. So we're just simply hitting negative log of 1 times 10 to the -12th, negative log of 1 times 10 to the -6th, and negative log of 0.001. When you hit those, let's check our answers. When we have 1 as our base unit, 1 times 10, we can look at this power of the exponent and know our answer. Did you find 12, 6, and 3? because this number is 1 times 10 to the negative 3. So here we have a basic solution, a slightly acidic solution, and a much more acidic solution. And again, I'll say when this value here is a straight 1, we can look at the power of the exponent. If it's any other number, we have to hit it on the calculator. It's not that easy to see, but it's the same process. Negative log of 001 is 3. Negative log of 1e negative 6 is 6. And negative log of 1e negative 12 is indeed 12. This makes a great place to pause our second lesson. We'll come back when ready, talking about ocean acidification.